All right, hello everyone. Happy Thursday evening / afternoon. We are here today to talk about LaTeX with the amazing Dr. Drews. Today we'll be covering some advanced techniques, and we hope you enjoy them thoroughly. Just a quick note, few minutes before we begin. We will be recording this workshop. It's recording right now. By staying on this call, you consent to being recorded. If you stay muted and keep your camera off, you won't end up in the recording. So it's up to you how you would like to participate. We will post the recording onto our website and onto our YouTube page, channel, whatever you call that. This workshop is intended for experienced LaTeX users. If you have never used LaTeX before, we recommend you go check out our YouTube channel for the first 2 workshops in this series that will cover for beginners and intermediate. You will need an Overleaf account to do this workshop. Please go to overleaf.com to check that out and get started. Around 6:15, we'll have a Q&A session where you can ask any questions to Dr. Drews about LaTeX or anything else that he feels like answering. Until then, please keep your microphone muted just to avoid any strange noise that's happening. If you have any trouble with your code, privately message me or any of the AIChE Projects people, or you can also message the general chat if you feel other people might be having the same problem. Okay. We have just a couple more things to get through. We'll be having some upcoming AIChE events that I wanted to just shout out a little bit here. First, we have our GBM next Tuesday, I believe that is, at 6:30 p.m. We'll be talking about resumes. It'll be very fun. We also have AIChE, which is our biggest event of the year, happening on February 3rd from 11 a.m. to 4 p.m. At 11 a.m. we'll have the innovation competition, which all the project teams will be participating in. I'm very excited to see what everyone comes up with. And at 2 p.m. is the career fair, and we have lots and lots of companies coming, so I highly recommend you can check it out. And then on February 12th, we have a pen pal event with HKUST, which is the university in Hong Kong. There is more information about all of these events on our Facebook page, our Instagram, our Discord. Follow us everywhere. We're glad to have your eyes on our events. Okay, so that's all out of the way, and here we are welcoming Dr. Drews, the renowned LaTeX expert, to teach us some more about LaTeX.
Okay, thanks, Eleanor. Could you add me as a co-host so that I can share stuff?
I forgot to do that. Sorry about that.
Not a problem.
There we go.
Anybody looking at I think that image that Eleanor just showed up, that was the source of this image, which was sketched in my 114 class, and I absolutely love it. It's got kind of a White Walker vibe to it, but I'll take it. So that's now my official Zoom image. If you were here with us before, welcome back. If you're new to it, welcome. Like I said, or like Eleanor said, it's assuming that you've had a little bit of experience with LaTeX so far. If not, we've got those other ones recorded. So our topics for today, we're going to kind of round out all of the usual things that come up in STEM documents. So those will be chemical formulas. A useful one, actually, I don't remember if I covered it last time. SI units. Did I cover SI units before? I may have just said SI units are good, not actually done it. But we'll cover SI units too, because those are really useful. And then tables, cross-references, and citations. Tables come up semi-often, cross-references and citations. I would say cross-references on an everyday basis probably show up even more rarely than tables do. But when you need them, you tend to need them a lot. So we'll at least mention a cross-reference and a citation. If you're currently in our 176 class, not mine, but Dr. Opakwitz's and Dr. Zhang's 176 class, some of this will be a repeat of what we covered in there. But it's important enough that I want to cover it again, because even if you're not in that class, it's usually the more useful of the few topics that we have left. So I'm going to switch over to Overleaf. I am also, let's try and share that again. I'm going to put some background music on. Just yell at me if it gets too loud. It's the good old Skyrim background music, so we've got that. Let's change this. Okay, and then I'll pull up chat too, just so that in case anybody needs to yell at me because it's too loud, I'll be able to see chat. So we're going to start with the two shorter ones, which are chemical formula and SI units, and then we'll kind of build those up as we get to tables. And I just wanted to briefly mention something that Eleanor had touched on with her, what was it, resume workshop. There are templates for resumes inside of Overleaf. So if you ever go to new project, you can come down to resume CV. And it will take you to a bunch of templates that you can use for resumes and CVs. So if you click on any of these, it'll open a new Overleaf document for you, and it'll have this resume in there, and you can kind of go through the source and modify your information as you see fit. Just take it with a grain of salt. These are not, unlike the packages that are inside of LaTeX, which are usually produced by organizations that have particular style guidelines. These are just put in there by users. And so, I mean, personally, I would not change the background color of your resume from white to gray like John Doe did over here on the right. So just take them with a grain of salt. They may not be perfect. They're all user generated, but you can find some pretty good ones in here. I mean, there's just tons and tons of them in there. Like I kind of like that one because it's nice and simple. Anyway, different option if you wanted to do that, but we will just be doing a blank one today. We're not doing a resume inside of Overleaf. So I'm going to go back here to the home and click new project, blank project. And I guess I would note one other thing that Eleanor mentioned. We're using Overleaf, but just keep in mind LaTeX is free and it's open source. So you can always install it on your personal machine for free. Overleaf is also free if you just want your own individual account, and it's not restricted in any way. It's got all of the usual features. It's just the bells and whistles of Overleaf are not available for free accounts. But you can always install it for free on your own machine. I guess this is just workshop 3, so we'll call it workshop 3. Go ahead and let this load. We're going to use the file browser over here on the left in a little bit, but for now I'm going to minimize it so that we can just focus on the source code and the compiled document. So I'm going to delete all of this so that we can just start from scratch, because we don't need all of that. And I want to keep it to just the bare minimum. A few of the things that we're going to do, I will be doing this time just so that we can see things okay over on the compiled document. So I'm going to use a 12-point font, and our document class is going to be an article. Most of our document classes are articles. And then if we wanted to begin and end our document, we would have these two elements. So again, keep in mind that the general structure here is that the begin end document is defining the body of our document, and the stuff in between the document class and the article, this is our preamble. And so our preamble sets what the document looks like, and the body is the actual content. Occasionally you need to do something in the body to modify the way the document looks like, but not very often. And that's the general structure of any LaTeX document. And so if we just wanted to say hello world down here, that would be our initial document. So a few things that I'm going to do just to make the document easier to view on this workshop is I'm going to change the margins so that all of the text is sort of grouped in one spot so that I can zoom in on it and we can still see everything. And so I'm going to say use package. I'm going to set the margin pretty big. I'm going to set it, let's set it to 2.5 inches. And in order to do that, I'm going to use the geometry package. And then I'm going to change the font, or technically I'm changing what's called the typeface. So if you ever have to search around for different typefaces, which most of us consider fonts, we will generally find them as typefaces. So I'm going to use the good old math PTMX, PTMX. because that's going to give us a Times New Roman typeface, which is going to be useful to us whenever we have to do math, because the symbols of the Math PTMX typeface have been sort of optimized for mathematical symbols too. So in STEM, it's nice to find packages that are optimized for math. There's two more. I don't remember the actual name of the package for Garamond. It might just be Garamond. That's a good one. And then Stix2 is another good one. I like Stix. Stix stands for the Scientific and Technical Information Exchange, I think. But these folks do nothing other than how do we make a really good looking font for STEM fields. So, and they've done it twice, hence the 2 in Stix. But I'm a fan of Math PTMX because it's just a nice clean font. But Garamond is okay, and Stix2 is pretty good too. Stix2 is a little rounder than Math PTMX. But those are pretty much the only 3 fonts that I ever use, or 3 typefaces that I ever use. And then we're also going to use Lipsum. And Lipsum is the one that we're going to do just to get some blank filler text. So if you say /Lipsum 1 to 2 inside your document, you'll get 2 paragraphs worth of filler text. And we're just going to do that so that we can kind of see how all of our stuff works as it goes. And those margins are actually a little bit too big. I'm going to reduce the margins down to 2 inches just so that we've got, a decent looking paper. There we go. So we can see everything. Normally you would never set the margins to 2 inch, right? You'd set them to like 1 inch, something like that. So let's talk chemical formula. There's usually 2 times that we would use chemical formula. It would either be because we want to write the chemical formula somewhere in like the actual text. So we would want to be able to refer to like C2H2 or H2O or something like that. Or we might want a chemical reaction. What we're not going to do is figure out how to draw the chemical structures. I think there might be 1 or 2 packages in LaTeX that may allow you to draw stuff like that. But drawing, after all of the time that I've been using LaTeX, I've only now started to kind of investigate drawing in LaTeX because it's usually so slow. You have to actually code what you want things to look like. So you have to code, I want a line from these coordinates to these coordinates. And so it looks great when it's done, but it tends to take a really long time. So I don't know much about drawing. So we're just going to focus on how do we sort of write chemical formulas. The package that we're going to use to do that is called MHChem. And normally when you use packages, you can combine packages like this. So if I wanted to say use package math PTMX comma Lipsum, that's the same as calling 2 use packages, unless you want to give it an optional input argument like we did here with geometry, and then it has to be on its own separate line. MHChem usually needs an optional input argument of version equals 4 so that it knows which version it needs to use. So MHChem will be our chemistry package. So I'm going to say Lipsum of 1 to get 1 paragraph. And let's say we wanted to write a chemical reaction. So a chemical reaction would be embedded inside an equation environment. And we went over equation environments before. And then I'm going to just throw Lipsum after this to get another paragraph, just so that we kind of see how it looks inside of a system of text like that. And then in order to use a chemical reaction, the MHChem package gives us the CE function. So I think that stands for chemical equation. At least in my mind, it stands for chemical equation, because I'm not actually sure if that's what they want. And so you would say /CE and then an open curly brace, and then you would write your reaction in here. So I don't know, maybe it's a dehydrogenation reaction, and you want to go from C2H4 down to C2H2 plus H2. I would write C2H4 and then a hyphen and a greater than sign, means arrow, and then that goes to C2H2 plus H2. And if we look over here at our compiled document, it did a bunch of that for us. So it knew that the C2H4 it should have a subscript 2 and a subscript 4, and same way for C2H2 and H2 as well. It knows the fractions too. So if you wanted this to be 1/2 out front, and I don't know, this one maybe like 7/8, something like that. Something like that. You just have to make sure that there's a space in between the two, and it will know that those are supposed to be fractions that go out in front. Does it put the plus and the minus signs in the superscript? I'm not sure what you mean by a plus and a minus sign in the superscript. Like if you want to charge or something like that? Oh yeah, for ions, yes, it can do that as well. And that was actually one of the things I was going to use the MHChem as an example of where to find that sort of information. This is sort of like the basics, and you can imagine you can do a fair amount with just something like that. So, right up above this, if we wanted to include that within our text, we could say something like the dehydrogenation of /C2H4 to form C2H2 and /CH2 proceeds according to the reaction, blah, blah, blah. Something like that. The CE can be used either within the equation environment or outside of the equation environment. And so now we have a way to write these chemical formula actually in the text somewhere. And those are sort of the basics. And that's a lot of what most of these workshops have done, right? They've introduced you to, here's the general way to do it. But if you need to learn more about like math or a specific package like MHChem or geometry, where do you go, right? How do I figure out what's the syntax to put an ion in here? Or what's the syntax to put the radical in here, right? The little dot that goes above it, or something along those lines. All of the packages are hosted on a service called CTAN, which stands for the Comprehensive Tech Archive Network. And everybody Overleaf draws its packages from there. So anytime it updates a package, it goes and checks CTAN and then updates Overleaf. If you have your own personal version of LaTeX, then it's going to do it. It's going to have a package manager in it, and that package manager is going to go check CTAN and then pull any of the updates back from it. And so it's important to know where to get CTAN, where to find CTAN, and where to get the documentation on your packages, because that's where you're going to find answers to those kind of questions, like how do I do ions? How do I do how do I put text above the arrow, or make one arrow be bigger than the other arrow, or do a back and forth arrow or something like that? The easiest way is to just Google the name of the package. And since this is a workshop, I'm going to do Google and not Bing. So let's say LaTeX MHChem. And usually the first hit is the one that you want. You want to look for one that says ctan.org. That's the Comprehensive Tech Archive Network. And so you want to go there first. And usually when you go to CTAN, you'll get a page that looks like this, and you're looking for here under documentation, you want package documentation. The README doesn't really help. You want package documentation. And different packages will have different documentations, but they will generally all look something like this. Oh, that's the MH. And MHChem, apparently it was made by a guy named Martin Hensel. So there you go. That's where the MH came from in MHChem. I had no idea. Presumably chem means chemistry. I think we can rest assured that this means chemistry. And then you look under the contents, and it's basically everything that you would ever need to do with chemistry. So equations, formula, charges. So, if we wanted to do ions or something like that, presumably that's under charges. And we can see a couple of examples here. If we wanted H+, we would just say H+. If we wanted 2-, then we do the little caret with a 2-. If we wanted brackets, et cetera, et cetera. It gives a couple of different ways to do it. I would probably tend to use this form where it does a double bracket. Looks like oxidation states are exactly the same way. So we can go ahead and try one of these. Let's say we wanted, I don't know, this H4 has some weird 2- on it, which I don't think it would actually ever have, but we can throw that on there and get a 2- on our C2H4. So to find out more about the package that you're using, check its documentation. Most good documentations will have examples like this. And usually they have enough that you can see like, oh, okay, that's what I wanted to do, and then just sort of duplicate it over in yours. And that's pretty much all I've done to ever teach myself anything in LaTeX is just check its documentation. The tricky part is usually finding which package I need. And then once you know what the package is, remembering the name of the thing that I'm trying to accomplish. So if it's chemistry, you can probably look through the contents here and remember, oh, okay, I needed radical dots, right? I knew that dot was called a radical. But if you just saw this and all you knew was there was supposed to be a dot up there, it might be hard for you to start Googling around or binging around and figure out, oh, that dot is called a radical. Or, oh, that dot means an unpaired electron, and that's actually what I'm trying to write. That tends to be where the tricky part is for me, is just figuring out the name. It's not so hard in math and chemistry because most of the time we know what those things are called, but it gets harder when you're trying to typeset a document and you don't know, I'm trying to make the word figure bolder than the actual numbered caption that comes next to it, and I don't know what that's called. That's where, make some tea or something and just start searching, because it can take a while to try and figure out what that is actually called. Okay, so that's the MHChem package. You can put that inside of math if you wanted to as well. So if we wanted this to be like X sub C2H4, like this was a mass fraction or something like that, and maybe, I don't know, Y sub CeH2, you can put that in there as well. And so here I've used the dollar signs to define an inline math environment. Oh, I forgot one of my brackets here. Right, and so now you can get those nice subscripts of like Y sub H2 or X sub C2H4 or something like that. And it does the automatic like double subscripting of C2 and H4 for you. So you can get nice things like that. So that's MHChem. Another one that I use a lot is SI Unit X. So I'm going to add another package up here of SI Unit X. SI Unit is exactly that. It's how do we get SI units? And the X just means it's an extension. So there used to be a package called SI Unit, and then that was around for a while and everybody decided it's really good, but we can do more. So they made another one and called it the extension of SI Unit. And so now it's called SI Unit X. SI Unit X gives us two functions. It gives us, on the one hand, /SI with a capital, and the syntax here is numbered followed by unit. And it also gives us lowercase /SI, which is it just gives you a unit. So sometimes we want to actually define a number with a unit, but other times we want to, for example, define the units on a variable. So maybe a heat capacity has a unit of a joule per mole per Kelvin, but we don't actually have a number there. And so that's the usefulness of the lowercase /SI, where we just give it a unit. That's how we could potentially use that. If we're actually giving a number with a unit, then we would use the uppercase version where we have two input arguments. The first one's the number and the second one is the unit. That is not all SI Unit X can do. It can do a lot more. Basically anything that you can think of with a number, SI Unit X can help you format it. So occasionally I find myself using another one from here, which is /num, which is kind of the corollary to /SI, right? The capital /SI requires a number and a unit. Lowercase SI is if you just want a unit, and /num is if you just want a number, right? So you want like 1e to the 10 or something like that. So I'm going to get rid of my second lip sum and say something like, Avogadro's number is n sub a, and then I want this to be 6.022 times 10 to the 23rd. And so I would say /num 6.022 E23. So that's its syntax for scientific notation. And if I say something like that, it will automatically format that to be the standard scientific notation. Of course, you can go in there and change it if you don't like times 10 to the 23. If you like actually E plus 23, you'd have to check the SI Unit X documentation, and it'll tell you how to do something like that. If we wanted to use that other example that I had just mentioned a moment ago, so the units of heat capacity, which is usually C sub P, are typically something like, I could say slash lowercase si and say joule per, let's say mole per Celsius. Celsius is a good one. And so that slash SI will then typeset this as SI unit or SI nomenclature for typesetting units. So it always does the power in the top for each one. You don't have to worry about the degrees on the Celsius because there's just a function called Celsius. The per here is how you designate something being in the bottom. You can raise things to arbitrary powers, but I'll let you check the documentation for something like that. And then if you wanted to use a number, maybe you would say something like the density of water is, this time I'm going to do capital SI, and the density that I'm going to use is, excuse me, about 1,000 kilograms per cubic meter. So I'm going to say 1,000 slash kg per m. I think I have to actually say cubed here. I don't think there's a shortcut for saying cubed, but there are several different ways that I could write that. So kg per meter per slash m per cubed is one way to do that. Another way would be or slash SI 1,000 slash kilo slash gram per cubic meter. Right? And I'll get exactly the same thing if I do that. It just, if you know the shortcuts, it makes it a little bit faster, but you can always just spell out, you know, prefix unit, prefix unit, prefix unit, prefix unit, all the way through. But if you check the documentation, you'll see that they have shortcuts for the most common ones like kilogram and meter. And so it's a little bit easier to find those. Kelvin, joule, most of those can be abbreviated so that you don't have to actually spell out joule or something like that. So that's SI Unit X. I use that pretty frequently, I guess maybe a little bit more than you might use it on a homework, because when I'm writing a homework statement, I typically have to define the units. And so I use the units a lot. And it's great to have them all in one place, and I don't have to worry about, you know, trying to generate them or anything like that. SI Unit X is, as the name implies, just for SI units. It's not for, what would that be? Imperial units, but you can hack your way to a collection of imperial units if you want, because the SI Unit X package allows you to declare your own units. You can actually declare your own subset of units with all of their own functions if you want to. I usually don't bother with that. I think I did it once just because I was like, that's so cool that you can do that, and then I never bothered again. So you can do something like, up in your preamble, declare an SI unit. That will allow you to now declare anything that you want. So you declare the function first, and then you declare what you want the symbol to be inside of the unit when you actually write it. So for example, if I want to declare feet or foot as the imperial unit, I would say /foot, because that's what I'm going to use as a unit. And then in closed curly braces, I would say feet, FT. Maybe I want Fahrenheit. So I could say declare SI unit slash, this one's kind of hard. I've never come up with a good abbreviation for Fahrenheit, because you can't actually use F, because F is a farad, which is a unit of capacitance. So it won't let you do this. But I would like this to read as /degree F. If I wanted pound, I could say something like declare SI unit /LB. And then call it LB in here. And so now if I come down here and I want the density of water, I could say something like, what's the density of, I think it's like 62.3. Correct me. I don't remember exactly what it is in those units, but I think it's pound per foot cubed. And so that'll give me a sort of a hack around to get to something that looks like imperial units. And so that's the kind of thing where maybe I write up the top 6 or 7 or 10 or however many, leave it in a preamble, and then I just move the preamble back and forth between documents if I ever need it again, because it won't be retained when you start a new document. I think it's 62.3. Maybe it's like 62.7 or 67.2 or something like that. But it's in that region. You can do the difference between like pound mass and pound force by, putting a subscript on there, all kinds of things. You can imagine it gets pretty complicated. And that's only like a fraction of what SI unit X can do. Like it's a any number or unit operation that you can think of, SI unit X can probably do it. It's also really good for the next topic, which is tables. I'm not actually going to use it for tables right now because it adds a level of complexity that doesn't occur often enough that I think it's worth doing. So we're just going to talk about tables in a more general sense. Before we get to tables, one of the things that I think bugs me the most about tables is that they're often way too complicated. So if you see a table, most often you see tables in one of two places. They're either in a textbook or they're on the internet. Most people see them on the internet and they assume that because they're on the internet, that's the way a table is supposed to look, and they look terrible. Oh my God, so many of that. Once you see what a normal table looks like, and then you start seeing the way they look on the internet or in Word or something like that, it's just like, why would you do that? It's harder to make it look bad than it is to make it look good. There's actually less to a table to make it look good. Actually, I think there's a little GIF. Less is more tables. Let's check the images. Yes, the data tables edition. So if this little GIF over here plays, I'm going to let that play. So, that's the default Excel or Word, and it's full of colors. And so you remove all the fills. Absolutely every fill gets removed. The entire border gets removed. All of the bold and the italics and all that kind of stuff gets removed. You just do a nice, simple left align of text and right align of numbers. Make sure the titles are aligned the same way. Columns should be nicely arranged, right? You don't just leave tons of space. And then if you want to demarcate things, then you use white space to do that sort of stuff. None of which are default in Word, nearly all of which are default in LaTeX, which is great, right? If you ever need a table in LaTeX, almost all of those defaults to make an attractive looking table are already present. So we're going to learn what that looks like. If you want to see an example of what a table looks like and you're trying to kind of mimic one, I usually go to a textbook. So I've got this example of your separations textbook. We can see here's a table. It does not have very many lines, right? The only lines that it has one underneath the caption, one sort of dividing the headers up here from all of the content, and one down here at the bottom to say, I've reached the end of my table. And that's it, right? It's not all gridded up with vertical lines everywhere. Maybe there's a sum line in here, very subtle line sitting inside here, but it's simple, right? The simplicity of it is what makes it a good looking table. Here's another one that has even fewer. We can keep scrolling down and look for more tables. Here's one inside of here. It's just got the chemicals up at the top, and then each of the categories down here on the left. If we scroll down a little bit further, maybe we'll find even another one. There's a good one, right? Has one extra horizontal line up on the top, but even that is alternative here. But anyway, that's what a table looks like, right? It's pretty simplistic. Text is left aligned, numbers are right aligned, and you've really only got 3 lines on there. You've got the top line, a middle line to define the header, and then a bottom line to say, I'm done with the table. So let's see how we make this in LaTeX. We're going to use one additional package, and that package is called book tabs. And that stands for make a table that looks like a book, or make a table that looks like it does in a book. Everything else we need for tables is built in. So I'm just going to kind of mimic that table that we had over here, where we've got molecules on the left and then some property of the molecule on the right. Maybe we'll do like, I don't know, heat capacity and density or something like that. And I'm just going to make those numbers up because I don't know all of those numbers. So we're going to use book tabs. I'm going to delete my last lip sum to put in a table here. To use a table, we use a table environment. So begin table, end table. I'm going to ask LaTeX to try to put this table at the top. And in fact, I'm going to ask it to try really hard. So I'm going to put the T exclamation point right after the table on here to say, ignore almost all of your rules and try to put this table at the top. There's an interesting, if you never noticed the pattern before, table captions always go on top and figure captions always go on the bottom. So let's find a quick, there you go. Here's a figure and the figure is up top and the caption is on the bottom. Here's a table, the table's on the bottom and the caption is on the top. It's just the pattern that I have no idea where that came from, but that's what it is. And so we're going to put a caption up on top and just call it my table of chemical data. And so that'll form a nice little like table 1 up at the top. And then we're going to say centering, and that's going to move our table away from the edge of the page, put it on the center of the page. And then we're going to start a new environment called tabular, begin tabular and end tabular. This is where we actually enter the data of our table. An extra argument that's required for the begin tabular environment is to tell it how do we want these columns aligned, right? Do we want them left, center, or right? And the number of characters you put in here defines the number of columns that come in this table. So we're going to have chemical, and then let's say density and heat capacity. And so we want this to be left aligned, right aligned, right aligned, because it's going to go text, number, number. And so we're going to say left, right, right. So lowercase l, lowercase r. There is a difference between uppercase and lowercase, and I don't remember what it is. So go check table documentation. But there is a difference on here. So we want left, right, right. Remember, the general format of any table is to have only a handful of lines, right? Let's go to that other more common table that we saw down here a moment ago. Right, there's a top line, there's a middle line, and there's a bottom line. That's the only 3 that are generally ever there. If you need to make the line that only spans part of it, like this kilomole per hour, just Google LaTeX, make line across only a few cells or merge cells or something like that. There's a way to do that too. The name for a line in a table is called a rule. It's not called a line, it's called a rule. And so book tabs gives us the most common ones, which are top rule, mid rule, and bottom rule. And those are pretty much the only 3 that I ever use. I use a top rule, I use a mid rule, and I use a bottom rule. In between the top and the mid rule is the headers, and in between the mid rule and the bottom rule is all of the data, right? The rest of the table comes in through there. So what we want our headers to be is, say, like molecule density and heat capacity. So I'm going to say molecule to say, here's what I want in one column and the next column and the next column. You use the ampersand on your keyboard, which is above the 7 key. You would hit like Shift 7 on your keyboard. So I want molecule and density and heat capacity. To say that I am done with this row and I want to go on to the next row, you put a double backslash at the end. So molecule, heat capacity, density, and heat capacity. And now I can actually start to write each one of these. So maybe we say water and 1,000 and what is it, 4.12, I think, 4.14, I can't remember what it is, 4.1 something for water. And then what else do I know off the top of my head? Ethanol? No, I don't know methanol very well. let's do methane, because I know its density is close to 1. I think it's like 1.2, something like that. I have no idea what methane's heat capacity is. I'm going to say it's 6. Just pulling that number out. I have no idea what the heat capacity of methane is off the top of my head. So that's our basic table. So if you've got this and you go ahead and compile it, we should have all of the major elements of our table are present. So it's got a top rule, it's got a mid rule, it's got a bottom rule. If you zoom in really close, Booktabs does what it's supposed to do with the table. The top rule and the bottom rule are actually slightly thicker than the middle rule, and that's considered good style for each one of these. But now, of course, you can throw all kinds of variations on here to make this as complicated as you want. So maybe underneath, or maybe you want the density to specify that the units are kilogram per meter cubed, right? So you can use the SI in the top rule up here. If you don't like density, if you would rather that be the Greek letter rho, you can use the math up inside of there. If you don't want to use actually water down here, you can use H2O instead. If you don't want to use methane, but you would rather use /CeCH4, you can do that as well. And so you can add all of these additional complications as you go until you get the table the way that you want it. Typically, the units always go in the header. They don't go along with the number in the actual table. Units always go up on the top. If you need 2 lines up on the top, you kind of have to, in your header, if you want like, name and units underneath it, you kind of have to hack your way around that. There's no rule that says that in between the top rule and the mid rule, you can only have 1 row. And so I could have added another one in here if I want something to be, if I want to say molecule, and then instead I want row up here. And I want the units underneath it, I would do something like this, where I have the row up top and maybe C sub P for the heat capacity. And then I would replace this with something like /SI, what is that, joule per mole, let's say per kilogram per Kelvin. It's a good set of units that we've got here. You can do something like this, where you don't have everything in 1 row. You can actually have 2 rows up there. Sometimes that will look a little bit funky, as it does here, because the row kind of feels like it needs to be centered. And so you just have to play around with, what do I want those to look like? That honestly, to me, looks pretty good. It's kind of weird to see molecule. So if you ever need a blank space in there, you can just not type anything there. If you just delete one of those, it'll assume that cell is empty. And so that's how you can kind of play around with some of those double subscript or double height rows. It's not really a double height row, right? It's 2 rows and you just left one of them blank. So that's tables. You can imagine they just get more complicated, but it just depends on what you're trying to accomplish. That's all of the major things that I've ever done in a table, right? It's text, math symbols, units, and numbers. What else is in a table? I mean, you can do weird things like tables of images, but usually I have to Google like LaTeX put images in tables, right? Because I don't do that often enough that I don't keep those instructions in the back of my mind. If you have to actually, let's not do that. I think I'm actually going to skip cross-references because I would rather spend more time on citations. And then if we have time, we can come back to cross-references, because I would say if we're focused on homework, right, the generation of homework or reports or something like that, we don't use cross-references very often. It's not like you're doing chapters worth of material where you have to keep cross-referencing back and forth. Usually you're just writing equations, right? And then you've solved the problem and you're done. You don't need to then refer to those equations all over again. So I think I'm going to skip cross-references. and focus on citations instead, because I think more reports will come up where you as a student need to write a citation, and fewer that you would actually need a cross-reference. And we've got like maybe 20 minutes before we want to get to the Q&A. So if we can cover all of the citations in 20 minutes, great, and we'll do cross-references, but I think we'll go with citations for now. So first of all, what is a citation? A citation says, I didn't come up with this. It's very important when you're considering academic integrity. You can sort of use the ideas of somebody else as long as you cite them. Different fields have different requirements for how you would use a citation. And so since this is an opportunity to talk about academic integrity, I thought I would bring it up. Within STEM, so any science, technology, engineering, or math field, the one thing that is never okay is to use a direct quote, except in extraordinarily rare circumstances. Extraordinarily rare meaning like, I'm going to prove somebody wrong, and I need you to know exactly what they said so you know exactly how wrong they are. You can imagine that doesn't happen very often. And so it's every other time that we use a citation, it's usually we're taking somebody else's work and we are reinterpreting it in our own words correctly so that we maintain their ideas, but we are not using their own language. So don't think of citations as a way that, hey, great, I never have to write another original thought ever. I can just go find somebody that wrote it right the first time, copy paste it and cite it, and it's like a get out of jail free card. That will generally count as plagiarism in any STEM class, and you don't want to bump up into that area of plagiarism. So just as a general sense, LaTeX will not stop you from doing that, but I wanted to, soapbox for a few minutes because it's important to me. And it's important to us as engineers, right, to give credit where credit is due and not to steal the work of other people. So never use a citation with direct quotations. It doesn't matter if it's cited or not, it usually still counts as plagiarism. That said, let's talk about how to create a citation. The first thing that we're going to do is collect all the information for the citation. We're going to ask LaTeX to typeset our citations according to whatever style we're interested in. So, like ACS style, or I'm not going to lie, I don't use much other than ACS style, so I don't know what the other styles might be. What are those other ones that they always ask for in like other like if you're in a literature class or something like that, throw some styles over in the chat. APA, MLA, exactly. There you go. Those are two very common ones. We're in STEM, so I use ACS a lot, but you can just ask LaTeX to format it as APA or Chicago or MLA or whatever. Yeah, ACS is American Chemical Society. And so obviously that's nice, right? If you've ever done that before, it's a huge pain in the neck to go through by hand and like set the year to bold and set the version to italics and put quotes around other things or underlined around other things. It's nicer in LaTeX if you can just say, here's the information. LaTeX just typeset it the way that it needs to be. And so that's what we're going to do. And so for probably the first time, we need another file over here other than like a figure or something. So you're going to click on new file up here. And it's not even a .tex file. So we need to, it's called a .bib file, which is our bibliography. You can name it anything that you want. I'm in the habit of naming it reflist.bib, but you could name it, I don't know, like giggles.bib if you wanted to. It can really be named anything that you want. It doesn't have to be named reflist.bib, but I try to name my files descriptively because if I come back to this in a year and all I see is giggles.bib, I'm probably going to kick myself from a year ago for not defining it a little bit better. So giggles.bib is what's going to hold all of the information about our citations. This is something nice because you can just have one of these and move it from file to, or from project to project. And if you don't use the citation, it doesn't cost you anything, right? It'll just sit there and it's not used. The problem with giggles.bib, the format of your bibliographic entry file, is that it's very sensitive to syntax. And so you got to be really careful with the way that you use syntax because it will break the entire document if you forget a comma. So I'm in the habit of copy pasting an awful lot because it gets the format the way that I want it. Whenever you want a new entry in here, you start that off with an @ symbol. And then whatever comes after the @ is the type of entry that you have. So for example, if it's a journal article, you would say @article, and that tells LaTeX what's going to come next should be formatted like a journal article. And then you use an open curly brace and say, what do I want to be able to refer to this as when I'm using it, right? I need a tag or a label or something like that. I'm in the habit of labeling them as like author and year published or something like that, or maybe like author and topic. It just depends on how many of these you have, but you can come up with your own labeling system. So I'm going to call this one Jensen 1987 because it was authored by somebody named Jensen and it happened to come in 1987. But it could have been Jensen 1987 bubble bath, right? If that's what they did in 1987 was they created a bubble bath, you can put the word bubble bath in there. It really doesn't matter. No spaces or underscores or hyphens or anything like that. And then you put a comma. Don't forget a comma. I'm going to close this bracket down here before I forget. So that will close all of the data that's inside of there will be here inside of @article. How did I get the .bib file? I just made it. So I went over here and said add new file, and maybe it's refless.bib or whatever you want it to be. You can call it whatever you want. I'm only going to use one. I'm not going to use two. You can have more than one, but it gets confusing. And so everything underneath here is all of the entries for that information. So for example, author, the .bib is special because we're going to have a package later that's looking for a .bib file. So it needs to have an extension of .bib so that when it goes and looks for it, it knows that the syntax of this follows a .bib syntax. So we're going to say author, and then to define the author, we do an open curly brace. Usually in STEM, we abbreviate the first few digits and then say something afterwards. So this would be KF Jensen. That was the author of this paper. Don't forget this comma that sits there. I frequently forget that comma, and then it breaks everything. And then I have to come back and fix the comma, which is annoying. We're going to say journal. This is chemical engineering science, comma. Notice I'm using curly braces for each one of these. We're going to do the same thing for volume because that's 42. We're going to say the issue number here is 5. The pages that this exists on is 923 to 958. And the year that it was published is 1987. And then it's still another comma. So we put a comma after each one of these. If we wanted to, by the way, the order doesn't matter here. If you wanted to do journal author, year, number, pages, something like that, that's okay. This information can come in any order as long as it's present. So for example, if I also wanted to include the title of the paper, these guys did something like microreaction engineering for photonic materials. I'm shortening that because that's not actually the title of it. I just don't feel like typing out their entire title. So that's one entry, right? I would like to be able to cite this somewhere. You can do more. Obviously, you're going to have more than just those two. So for example, maybe I wanted to cite a book. I would start off the same way, right? @book, open, closed, curly brace. The first thing that goes in here is whatever I want to refer to the book as. So maybe I'm looking for batch distillation in that Cedar textbook. So this was Cedar's textbook, and they talk about batch distillation in here. So maybe I would say Cedar batch dist, because that's what I want to be able to refer to it as. And then I can include a lot of the same information. So the author here is J.D. Cedar and E.J. Henley, and let's call it A.D. Drews, which is most definitely not the case. I did not write that textbook at all. But just to demonstrate the syntax here. If you have multiple authors, yes, they do need to, this was not a question, but I know you're asking it. They have to be separated by the keyword and, They will not show up as and, but and within a .bib file is recognized as a keyword. And so that's how you get appropriate usage of multiple authors, appropriate handling of multiple authors. So you cannot comma separate these or semicolon separate these and expect to get the right results. They might print, but they probably won't be printed correctly. So there's our author. The title, I'm just going to call it Separation Processes. Separation Process, okay, Principles, I lied. The year of this was 2010. The publisher is usually what we also need for a book. So this is John Wiley and Sons. And then the address of the publisher was New Jersey. And we'll just go ahead and give pages because maybe we want folks to know specifically what pages of the textbook we're interested in. And so we'll say 476 to 477. But again, don't forget the commas after each one. And don't forget to use the curly braces to include, to specify the information. There are different syntaxes of .bib files where the braces are not necessary, but this is the only form that I've always been able to use, and it's always successful. So it's the only one that I use now because I know it's successful each time. And then you can keep adding more and more and more and more and more as you want. However many references you have. Books and articles are the most common. If you need to know like how to cite a website or something like that, then you just start Googling LaTeX website citation format, and it'll give you examples of what this kind of stuff looks like. So that's our .bib file, and now we have to switch back over to our tex file and actually tell LaTeX, okay, I would like to both put the little number in as well as generate the bibliography. And so that's what we'll do in our remaining 10, 15 minutes or something like this. But I'm just going to take like another 30 seconds or so and leave this screen up because if you don't have exactly this information, it could either just plain old not work or you won't get the same result that I have. So I'm just going to leave this up for till 6:02. It's 6:01 and 30 seconds. We'll just wait for another 30 seconds here in case you've got a little behind. The @ is just special syntax for entering bibliographies in LaTeX. @book means LaTeX, when you go in here and see this information, it should be typeset like a book would typeset it. So it will say, okay, this is a book and you've asked me to do MLA style, so I'm going to format it according to book MLA style. If it said @article and you had asked LaTeX to do APA style or Chicago, it would say, okay, take this article, here's the information, filter it through the APA style and typeset it correctly. Otherwise, it won't know, is this a book or a website or an article or something like that. @ just happens to be the special symbol that it uses. Okay, let's switch over to the main.tex now. And we're going to add the important stuff first, and then we're going to come back and we're going to add some stuff that says like, ooh, that looks pretty. So the key one to use is a package called Biblatech. So this is use package Biblatech. That's the one that actually says, let's make ourselves a bibliography. Usually we have to include at least one optional input argument to this. And part of that is to say, which backend do I want? There are different backends because different people develop different citation styles as you go. Honestly, I don't know what the difference is between all of them. So I'm just accustomed to using backend equals, it's pronounced Bieber. I have no idea why. It's not Justin Bieber, but we're just specifying the back end is Bieber. There are different backends that have different behavior and different functionality. This is the only one that I use because it works all the time for STEM. So just always leave backend Bieber because it works. And then you can also specify things like style. So this would be chem.acs. Right, that's the one that I use most often, is the American Chemistry style, or American Chemistry Society style. And so I use chem-acs. What would you do if you wanted to use another one like APA or MLA or something like that? Google Biblatech use MLA, right? Or Biblatech use APA, or Biblatech Chicago style or something like that. And that would take you over to CTAN, the archive network, and then you would check its documentation and say, what do I need to write here, right? Style equals what for all of the different ones that I might have. But again, I use ACS most often, so that's the only style that I know off the top of my head is chem-acs. Underneath that, we have to tell it which file to use. So we have to say add Bib Resource, and then specify the name of that file that we just wrote. So this was giggles.bib. So the first one just said, get ready to use our bibliography style. And here's the backend and the style that we want to use. And then the second one said, when you go to search for these citations, go look in giggles.bib. And that's where we'll find it. So that's sort of our bare minimum up here. And then when we actually want to use the citations down in our document, I'm just going to go down here and add a little bit more information down here and say something like, information about batch distillation can be found in Cedar. Right, and what I would like is a little citation number to come after that, right? Maybe it's a number in parentheses, or maybe it's a number in brackets, or maybe it's a little superscript. All of that would depend on whether you're using like MLA or APA or whatever. We don't really care at this point, because the way to get that citation in there is to use a function called AutoCite. And then the argument to AutoCite is whatever it is you named it over in giggles.bib. So over in giggles.bib, my Cedar batch distillation was called Cedar batch dist. And so I'm going to copy that, and I'm going to come over here. And I'm going to put that inside of there. If you have some autocomplete tools turned on inside LaTeX, this will actually autocomplete, and it'll go check your bib file, and it'll kind of show you, here's the things that could be that name. But I'm in the habit of turning all of my autocompletes off. So I just copy paste them as I go. So that'll give us the little number. And then the last thing that we need is to actually give us that summary of all of the citations that we used. And so that's easy. Wherever you want that, you say /print bibliography. And it will print the whole thing. And it will only print the ones that you have used. So for example, right here, we've used only Cedar batch dist. We haven't used the other one, the Jensen one. And so Jensen is still sitting there in giggles.bib, but we didn't actually use it. And so if I look down here, let's scooch this over and zoom out a little bit. We see we got what we wanted, right? We got information about batch distillation can be found in Cedar, and there's a little 1 that's sitting up here. And then we got this new thing that says references, and we have our number down here, and it's all been formatted correctly, right? It's got the last name, comma, first name with a semicolon, last name, comma, first name with a semicolon. The title's in italics. It's got a colon in between the editor and the place it was published, and the commas are all right. It used PP instead of pages because that's what it did. It did it all automatically, and I hate doing all of that stuff manually. I'm sure if you've ever done it for more than like 2 examples, it's been equally frustrating for you. And so if we wanted to keep going after this, maybe we could add another citation that says something like microfluidics are described in another paper, right? We don't have to put the name on there, and we can say /AutoCite Jensen 1987 and put the period afterwards. And if we hit compile, it'll just automatically update our citations list, and it'll automatically change the numbering so that we get a 2. It even did the correct placement of the citation. So the number itself always comes after the period, And so if you look at the way that I wrote it, I did it both ways, right? The first time I put period followed by autocite, and the second time I did autocite followed by period. LaTeX doesn't care. It knows what you mean, which is I would like a citation to go here. And it also knows that according to ACS style, the correct formatting is for the number to go after the punctuation. And so it moved it there. It's so great. Every time I see it, I love it. It knew, you know, it's Jensen, comma K. It knows the title of the journal is italicized, the year is bold, the index or the issue is italics, blah, 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 blah. It's so great. Once you find the style that you want, it'll just automatically do it and it'll look awesome. A lot of the variations that you would have to do that beyond this, like, oh, I don't want these to be parentheses, I want them to be square brackets. It's usually set by whatever citation style you're using, like ACS says this should be parentheses. If you have to change that for some reason, you're just going to have to dig into that documentation and find out how to do it. I don't know how to change a lot of that by default. What I do frequently do is say, maybe I don't want this to be called references. Maybe I want this to be called bibliography or works cited, or I don't know. What else? That's pretty much the only two, right? Usually it's references. And so to do that, you can offer an optional input argument to print bibliography. And instead of that, you can say heading equals none. And that'll eliminate references. And then you can just put in your own section header, right? You can say something like section works cited. And so that's just kind of a workaround to say, I don't want you to use your built-in header. I would like you to say works cited or bibliography or whatever, citations, if that's what you want it to be called. So that's probably the most common modification. The second most common modification is oftentimes in articles, it's convenient to have the title inside of there. Notice it's always included for a book, but the journal article that we have here does not have a title, even though, I mean, the journal article does have a title, but our citation does not have a title. And so that is an optional input argument to Biblatech. And you can say that you would like the article title to be true. Article title equals true. And now it will print the article title. So it says microreaction engineering for photonic materials. That's kind of the only other most common one that I use a lot. You can do things like chapter title if you want more information in your book or something like that. So once you've got that thing set up, you know, the initial setup, everything that we just did, it's like, wow, that took 20 minutes just to do that. But you only have to really set it up once, right? Once you've got it set up, now your only goal is to just enter information correctly over here. And so it's a question of, is it easier for me to enter this information than it is for me to typeset it over here according to whatever format I want? And the answer is almost always yes. It's easier to just type this as its field entries in the reflist.bib or giggles.bib file and allow LaTeX to do the citing automatically. So that's citations. Like I said, we don't really use cross-references very much. And if you ever have to do more than this for a citation, I tend to have to Google it because it's probably fairly specific what I'm trying to accomplish. So, but that's all of the major stuff. That handles, 90% of all citations is just getting the information in there. And then we can let LaTeX do the rest. So we've got, I think, Eleanor, we're going to leave the last 15 minutes for Q&A, right? And we're pretty much there now.
So the last 15 minutes is supposed to be for, if you have any LaTeX related questions, you can ask the expert here, or you can ask Google, either way works.
Yeah, I mean, the answer from the expert might be, I don't know, you'll have to Google it. Like, it's in full disclosure. That's how I get a lot of my work done in LaTeX, when I have to make anything more than basic changes, especially if I've never made those changes before. So that could happen. So I'll open it up then. If you're all set, thanks for coming out. But otherwise, I'll just kind of hang out and we'll answer questions as we go.
Just as sort of a closer for people who are heading on their way out, thank you for coming. This is a very exciting event. It's also the last LaTeX workshop that we'll be having this year, because we've kind of hit the end where if you needed something else, you just Google it. And
pretty close.
Pretty close, yeah. If you haven't already, please sign in at that tinyurl.com/wi2121latex3. If someone could post that in the chat, that'd be great. And if you want to learn more about LaTeX, YouTube, Physics 87, just Google it. Practice by doing your homework in LaTeX. Your professors will love it. I'm pretty sure I got higher grades in Physics 2CL because of that. So
you really might. There's a what's that comic? I can't remember. There's a cartoon about this. LaTeX. No idea, but most beautiful thing. That's it. I can tell when Google starts auto-completing that that's the one that I want. Oh, there it was over on. That was it. That's only, there it is. Ignore the people in literally in LaTeX. It's not pronounced latex. It's pronounced LaTeX. So it's all these different languages, and this is exactly what it works. And then you get down to LaTeX. Is it widely used in things like textbooks? Yep. Pretty much every STEM textbook that you come across is going to be typeset in LaTeX. And you can start to recognize it too, right? If we go over to Cedar's book, like, I mean, with what we've got now, you can do the vast majority of everything that you're seeing in Cedar's book. There's one additional thing that we didn't do, which is custom environments. So you can define an example environment that's got this nice gray and it's got like a title and that kind of stuff. You can define down here. Let's go down to the bottom. Well, anyway, yes, they're used a lot in textbooks. So that idea of, you know, the problem statements are here and then the selected answers are in the back of the book and they have a particular name. All of that can be done automatically with LaTeX. The indexes, right? If you flip to the back of the book and say, I want to know where a certain page is, all of that can be done in LaTeX, and it frequently is. I don't know if I said it before, but it's also infecting the web now. So there's a very common package called Mathjax that's being used in browsers. And Mathjax is built on the syntax of LaTeX. And so it allows obviously beautiful looking equations that are on there, but it also gives you the ability to do like cross references and stuff like that, that are find their source in LaTeX. Are the files automatically saved? Yeah, at about roughly the same rate as I think they are on Google Docs or something like that. If you're using your own version of LaTeX, so on your personal machine, you'd have to check it. Most of them do autosaves, the same as like Word does or something like that. But yeah, most of it autosaves. You're welcome. I think LaTeX is great, so I'm happy to do this. For graphs, are they imported or made in LaTeX? So this is sort of where I'm at right now, is most of the time I make the graphs outside of LaTeX, but I'm slowly learning how to make them inside of LaTeX. And so the package that I'm using for that is Pgf Plots. Pgf Plots, and the gallery is a good place to go. And so Pgf Plots allows you to create them kind of with a syntax that's similar to how you would do them in MATLAB. So for example, you can set minimum and maximum of different axes, right? And I zoomed in 3 or 4 times and it zoomed in too far. It'll do that kind of stuff. You can plot just data, or you can plot, functions, and it'll actually draw the function for you. But this is, I still don't use it often enough that I'm familiar with all of the syntax. I usually have to come back to something like this to remember how to do it. But the advantage of this is that the symbols, it looks awesome, right? This is always the case. It's the most beautiful thing I've ever laid eyes on. It looks really nice. But the other thing is that it's actually a communication issue, which is if you create them all in LaTeX, you can get the symbols to look the same. And so if you have like f of x, it'll look exactly the same in the figure as it does in the equation. And that's important, right? If you've ever come across a textbook like this, and in the, over here it says c is equal to 4 and it's uppercase, and then you go look in a figure and it's lowercase, you have no idea if those are the same, right? You have to guess that they're the same and then probably do some kind of analysis to confirm that they're the same. And so there is an argument from the standpoint of clarity that it's advantageous to do it all in LaTeX. I'm just not familiar with it enough yet that I do it frequently. But the syntax isn't difficult, right? You add an axis and you say add a plot, and it automatically does what you're interested in doing. I don't do it a lot. So I would just point you to Pgf Plots if that's what you want to do. You're welcome. If you want to make drawings, the plots actually use exactly the same thing the drawings do, which is TICZ. TICZ is, it's quite a program. Overleaf's got, it's not even it's quite a package. It's all of the basic drawing things that you could think of. So it'll draw a line and give you the intersection point, but the syntax is just, this is why I don't use it. It does exactly what you want, but you have to tell it exactly what you want. I want a line to go from -1 to 2, and I want it to be solid, and I want it to go to 2 and 4. I want it to be gray, and I want it to have thickness of thick. And it's like, yes, all of that is great, but it's a giant pain in the neck if you want a particular curve and you don't care exactly what the curve looks like. You're like, I just want something that looks like a curve. You got to go find like a mathematical formula for it and play around with it until you get it right. And so I don't use TICZ very much because it's just faster for me to use virtually anything else. I would almost rather sketch it with the little Wacom tablet, even if it looks hand sketched, and then just import the sketch, because I'm just not good enough knowing all of these various commands on here to do it. But they can make great stuff. The most that I ever got to was 176 in the experiment summaries. Here's a good one. Yeah, so like these kind of figures. Right? They can make great looking figures, but it took me probably an hour and a half to figure out the very first time, how do I get this exactly how I want it, right? How do I get a figure next to a figure and the axes are square and they've got grid lines that are lighter than the outline, and this title's on the left and this title's on the right. They're aligned, you know, horizontally and vertically and all that kind of stuff. This has filled dots with a horizontal hash line and all that kind of stuff. It's fine once I've got it. Right now you can take it and copy it back and forth, but it's kind of a pain in the neck the first time around, and it's easier to just do it in like MATLAB or something and import it. But because I have to do this a lot, I'm taking the time to learn it. How long did it take to write the textbook? Not as long as you might think. I mean, once you get used to the syntax, it goes really fast because you can focus on content. And so the textbook, I mean, if you want to look at the source file of the textbook, it's not anything different than anything that we've done here. It was just subdivided by chapter to make it a little bit easier to read. I'm actually updating the textbook this year because I'm changing the way that it wrote. So this is the source file, and it's just, you know, tech file after tech file after tech file. And then if you go in and look at any one of these, so I use Text Studio for my own editing, but there's tons of them. It's one of the, if you have the thing on your own computer, it will compile a lot faster than it will through Overleaf, because you can kind of like leverage your computer to do that. So I don't have this one compiled, so we'll just have to look at the source code like that. But right, it's the same thing, right? It's just equation after equation. I use a lot of cross references in there because it's a textbook. That's what these labels are. But that's all it is, you know, section header, begin figure. I actually drew something with TXZ for the book. But there's nothing in here that, you know, we've really done, or nothing in here that we haven't really done other than a handful of like specialized things that don't come up that often. They're sort of specific to a textbook. But that's it. I think I have an example environment in here. Matrices, aligned equations, shaft work. Oh, I have to go back. Sorry, there's a jet going. This is an example of a custom environment, right? It's an example in a textbook, and I made it example. And again, that's the kind of thing, it's like, well, you don't really need to do that until you need to do that. There's no reason to learn how to create a custom example just to learn how to do it, because it's hard and you don't do it very often. But you can imagine in a textbook, there are probably 100 examples or more. And so when it comes time to now actually write the examples, it's a simple syntax. And so I get to leverage that workflow of LaTeX, right? I did all the hard work of here's what I want the example to look like. And then in the remaining 13 chapters, I can focus on the content of the examples, right? Begin example, label it, title it, and then just start working. And so it goes much faster, because if I were doing this in Word, I would have to go find a previous example and like copy paste it and then modify it again. And it's just easier to do this. So I don't know, how long did it take? I mean, start to finish, it probably took like 8 months, but it's not like 8 solid months, right? It's like, oh, I have 3 hours on one day a week to work on it a little bit. So you just kind of have to chip away at it as you go. You're welcome. You're welcome.
Yeah, we're coming up on the 30 minutes, so I think it might be a good time to wrap up, call it a night.
Sounds
Thank
good.
you, Dr. Drews. This was fantastic. I learned a lot.
You're very welcome.
Yeah.
For anybody in my class, we'll see you in class, and otherwise we'll see you when we see you.
All right.
Bye all.